Welcome to Science 9 in the AM. Shidaki here. We are with the Garys. We are wrapping up our exploration into voltage, current, and resistance. Resistors are just things that use energy to slow the flow of electrons down. And voltage is like the pump. If you think of an elevator that raises you up high so that you have a lot of potential energy, or an object high, and you can drop that object, it has a lot of energy to release as it rolls downhill or something. Well, voltage is the elevator or the pump that pumps up the electrons with energy. And then current is really easy to think about if you think about water flowing. It is the flow of electrical energy through the electrons in the wire circuit. Everything for it to work has to be in a circle, a loop. We've noticed that there's two general ways you can make these loops: a series circuit or a parallel circuit. We're going to just review quickly while we had series circuit. Then we looked at parallel circuit. And these are the last things we had. I'm going to pause the video because I think we stopped right here, correct? So we're going to add to our notes. When one bulb burns out, the other will still work. And we were running short on time, so we rushed through that. So I'm going to pause the video while you jot that down. Okay, so you've added that in, I hope. I'm going to retrace what we talked about yesterday. Yeah. Oh, it's basically that last sentence, right? When one bulb burns out, the other will still work. Series circuit, that didn't happen. When one bulb burns out, everything is on. So I'm going to follow it from the negative end. But I told you this more than once. Same logic if you follow it from the positive. Okay, I'm going to talk about voltage. 2 volts. That means an electron, the electrons that leave there, it's actually a cooling of electrons. It's a collection of electrons. We'll just think about it as one at a time. Anyways, they leave with high energy, 2 volts of energy. It's like raising a ball 2 meters, let's say. Then you can drop. Well, either it drops and uses up that 2 volts of energy through this, comes back, get re-energized from the battery system, or that set of electrons goes through the longer loop. It doesn't go through the other light bulb. 2 volts. Either way. And then let's think about the current. Electrons, say 200 milliamps. Well, let's say 200 liters of water leave in 1 minute. Well, 200 liters of water, if 120 liters go through this, I noticed my arrows the other way. That leaves only 80 liters to go this way. It adds up eventually in a circuit, in a parallel circuit. So the current in a parallel circuit, I think the logic behind that makes sense. You can't have an electron go through this and this. That's why it has to add. Once it goes through the first light bulb, it can't go through the second. That's why they have. Okay, that's current. In the series circuit, it was the voltage that added up the grand total. They behave differently. There's advantages to both. This is the one we use in our office. Some other things. I'm going to just talk about this. If we think of the battery, like, remember I was using a play structure before as the idea. Well, the batteries are like an elevator or climbing. You putting in the energy to climb up the steps, 2.5 meters, the top of the play structure. And then you've got 2 slides to choose from. You can either fall 2.5 meters down the first slide, that's like the first light bulb in the circuit, or you could walk over and do the second slide and fall 2. You can't do both though, right? We can talk about this like it's a speed. But like I said, most people have experience with play structures. That's the exact same analogy for voltage. I like the idea of climbing up on a slide, choosing one or the other. Remember, the series was one mini slide followed by another for voltage. So I want you to jot that analogy down. You can draw it as really simple as you like. I want you to be able to explain that. If somebody has asked you what voltage is like, I'm going to ask you later on a series or parallel circuit. Compare the two. I'll pause the video. Okay, I'll move it along here, and we're going to just review something here. What is a parallel circuit? A parallel circuit has more than one resistor. Anything that uses electricity, light bulbs in this example, gets its name from having multiple parallel paths, like parallel slides on a plate structure. Charges can move through any of the paths. If one of them in the circuit is broken, like one light bulb's out, no charge will move through that path, but the other paths will continue to have charges flow through them. Parallel circuits are found in most household wiring. I've said that. Now you're going to get it down on paper. This is done so that lights don't stop working just because you've turned your TV off. And I want you to write that paragraph. Exactly. And I'll pause my recording as you write it down. Okay, I'm thinking it's time now. Time to move it, right? So, we've got that down. You don't have to copy this next thing down because you have it, but I want to review it all at once. Compared to energy released when falling, this is the voltage. This is usually easier, and I've done this already, but I want to do both at once. In a series circuit, one bulb wired after another, first type we wrote. The battery is like you lifting yourself up with energy, up 1.5 meters on a plate structure. You take a mini slide first, 0.5 meter down. How much do you have left to fall? That's your potential drop, your voltage. You have another meter to fall. This is like the first one, then the second one. They might be the exact same break, and then they might be 0.75 and 0.7. Share that. You've noticed that the voltage is what makes the light brighter. It's a parallel circuit, what we just looked at yesterday. It was like you lift yourself up the play structure. You got two choices at that height. You either fall 1.5 meters down that slide or this slide. You can't do both. So you got equal energy falling down this slide, equal voltage. You got two light bulbs. And that's the best way to wire it. Okay. You didn't have to copy that down, but I just wanted to reiterate. Now, I had said textbooks out, and this is the time we need for textbooks. So I am going to open mine, Making Electricity, and I'm going to guide you through this page 269, and we're going to summarize together generating electrical energy. We are going to summarize right down as we read. Yes. 76. Well, start at 269. You're going to flip to that, and let's just see here. I'll pause. So we are going to read together. When we get to generating electrical energy on 272, we're going to summarize that. We're going to make some notes ourselves. So no, it's going to be in your notebook. So if you have a coil notebook, this is a good thing to put in your coil. Okay. I'm going to flip to 269 right here, same page, right? And I'm going to just move this so I can grab things easier. Let's see. I want the hand though. Makes it easier. Works. It's not working. Okay. Think locally. Hey guys. We're on this page together. So we're reading together. I'll start the reading. The Cowessess First Nation and Saskatchewan government are partnering to develop a wind energy project on lands southeast of Regina. The turbines will be able to harness wind 70 to 90 meters above the ground. So they're up high. More than 15 meters higher than other turbines in the province. The greater height allows the turbines to capture stronger winds and thus produce more electrical energy. The project will also use an experimental new battery that stores the electrical energy from the turbine efficient. This is an old textbook, so it's already done. Oh, didn't mean to slam through that quick. Also, the Crake Eco Center is another example of a renewable energy project. A renewable resource is one that can be reused or replaced in a shorter amount of time, I should say. For example, energy from the sun and wind. A non-renewable resource is one that can't be replaced once it's used up. Yes, you could wait a few billion years or something, a million years for oil to be done, but that's not renewable within a usable amount of time. That's right. Examples of non-renewable is coal and oil. So once you use up all the oil resources, and they're gone, right? Because it took millions of years to form it. Not only that, though, we have found over the years then that when you use oil products, gasoline, diesel, coal, when you burn it, there's environmental aspects that we don't really want. And that's an environmental problem, as well as the fact that once you use it up, it's gone. So, two reasons why you've heard about a shift away from non-renewable energy. Okay, local solutions to generating electrical energy. Flip the page like I have. Oh, I guess you guys have it actually right. Yeah, it is a flipper for you. Yeah. When you turn on the lights in your bedroom, you're using electrical energy that is generated far from home. A large or smaller scale hydroelectric dam, just on the picture there, you see there, or a coal burning electrical plant, generating plant, is probably the source of your electrical energy. Now, though, we've actually increased our gas, natural gas, too. It still burns fossil fuels, but it's a little cleaner than coal. Some areas of Saskatchewan, the source is wind farms made up of giant wind turbines. To build a hydroelectric dam or enough wind turbines to generate electrical energy for a large number of people requires a huge investment in people, money, and equipment. Usually governments and businesses build these larger scale projects. The one thing, anybody from Manitoba or lived in Manitoba? Okay, what are they, we call them power poles around here. What do they call them in Manitoba? I know somebody quite well from Manitoba. She always said, the hydro poles. Did you ever hear hydro poles? And they call it hydro instead of power poles because Manitoba Hydro, most of their electricity is generated from moving water. The one thing about hydro, it's definitely renewable, but when you build that, though, you disrupt the environment around that because you're damming up water to build up pressure up. But you can argue at least it isn't continually polluting the environment after that initial change. And it'll change the ecosystem around it. So there's always environmental studies done and what will this kill and what, that kind of thing, if they are going to build a hydro dam. But that's one thing, and it goes on and on and on. I'm going to skip the energy thing. Ask an expert. I'm not going to ask an expert right now. You could, though. Hey, isn't this 272? Yeah, that's the one we're going to, remember? Well, we'll read this. This is the one we're going to summarize. So we're going to pay special attention. That's sort of just an intro. Generating electrical energy. We said 270. Here, I'll show you what I'm talking about. It's okay. Summarize generating electrical energy on 72. So we're going to take note and come back to that. We will read to 276, as you know. Okay. So, 1831. So this is. We will, and we'll do it as a group. So I just want you to pay attention. And we'll read up to 76, as you mentioned. We'll come back. A guy named Michael Faraday introduced a way to generate a steady supply of large amounts of electrical energy. He demonstrated that an electrical current can be generated by moving conducting wire through a magnetic field. And if you guys recall, we did a mini activity with the compass magnet, right? The north, and then had electrical energy running through our wire. We noticed, yeah, electrical energy and magnetic fields, they have something to do with each other. I always call it two sides of the same coin. They are, it's like multiplication and division. They're related. And in physics, we call it electromagnetic phenomena. Like, we actually consider them one and the same, related. And I say we, people who study physics in universities. Okay? Anyways, conducting wire through a magnetic field, a process called electromagnetic induction. Today, We use electromagnetic conduction to generate electrical energy in generators. Most generators do the same job. They transform the energy of motion, kinetic energy, a type of mechanical energy. So if you've got moving, hey, thanks, into an electric current. The magnets inside the generator are rotated by a turbine. And it's a machine that uses the flow of a liquid, or of a fluid, such as a waterfall or fast-moving river, to turn a shaft. The magnets spin coils of copper wire. This pulls electrons away from their atoms and creates a current in the copper wire. The electrical energy is delivered to a transmission substation where a transformer boosts the generator's voltage for long-distance transmission. So the really, really big lines, have you ever seen, I'll just draw this and then erase this. Okay. In the city, in the area around Belfast, power lines are above ground. You don't have to draw this. If you just have a single power pole like this with wires running from the other, that kind of thing, or maybe just three. You know how often this has a T drawing. I'm not a great artist. And then there's the lines running through. Those are generally household voltages, or like they're not the extremely high. You know that they usually have warnings like around the high voltage transmission line. They usually look some kind of system like this, and I'm just going to draw. They usually have support, and then they have a lot of. You guys know what I'm talking about there? Have you ever seen power systems like that? That's the high energy lines typically are on those. And then they deliver it, we'll read more about it. But that's what they're getting at. So back to this. High volt generators for long distance transmission. The electrical energy is sent through transmission lines to reach cities and towns. The web of interconnections between generating stations, substation, and users is an energy grid or distribution grid. Went too far. Household voltage is typically 120 or 240 volts. When we plug in, like just regular stuff, those regular plugins are just 120. If you have an electric stove, it's 240. Dryers are higher. It's not a regular plug-in for a dryer. If you have welding equipment, you might have a different type of plug-in system too. For energy to be useful in a home or business, the extremely high transmission voltage needs to be stepped down again. Transformers step transmission voltages, which may be in the hundreds of thousands of volts, down to distribution voltages, which will be less than 10,000. And then there's little cans on the top of some power lines that then get it down to the voltage at your house. Generating electrical energy starts with a spinning turbine. Where does the energy come from to spin the turbine? That's all it changes, actually. Whether it's nuclear, waterfall, or like a hydro station, coal, gas, diesel generating, it all has the same general principle. So looking at this here, generating station. Could be in Amsterdam, coal. Could be somewhere with a hydro dam. There's a transformer that just translates it to the high voltage. Sends it out on those big stacks, like I said, you recognize. Then it gets to a substation where it dumbs it down to something safer for inside the communities and stuff. Sends it out. Underground electrical wire is possible. And in some areas of our city, they're above ground too. Transmission lines, transformers to your homes. That's the general thing. We're going to come back to this in a second. Using water to generate electrical energy. Most energy in Canada is hydro, which means it's generated by harnessing the energy of flowing water. Some hydroelectric stations use fast-flowing rivers to turn their turbines. Other hydroelectric stations, such as Niagara Falls and stuff, use the flow from a waterfall Many communities, such as Elbow, beneath the Baker Lake, do not have a waterfall, so they built a dam across a river to store water in the reservoir. The water from the reservoir is directed through the channel, called a penstock, to a turbine with ridges around it. The water turns a turbine which is connected to a generator. Look at that. Just taking a look here too. So the water flows in, and then it's sort of like a corkscrew type thing, but it swirls it around. As long as it's moving, then it's going to move the magnets and stuff, and the wire in this generator. That's what does the electricity. So in that way, and there's no fire, stuff like this, so it's not polluted. Using heat to generate electrical energy. If there's no waterfalls or rivers in your area, which is most of Saskatchewan stuff is not high. Well, mechanical energy can be used? Well, that's heat, thermal energy from steam. Many areas, thermoelectric generating plants use a fuel such as coal or biomass to heat water. Like I said, there's a movement to more natural gas. It's cleaner than coal. Coal, oil, and natural gas are fossil fuels, though, which means they were produced from organic matter of organisms that lived millions of years ago. Because of how they were created, fossil fuels are non-renewable. It takes way too long to consider them to have them come back again. In figure 8.8, you can see that a fossil fuel, usually coal, is burned to boil water. The steam is kept under high pressure in pipes, which allows it to reach higher temperatures than normal. The high pressure steam strikes and pushes blades on a turbine. Coal is used to fuel the Poplar River power station near Corinth. Now, I say Estevan, it's Estevan area, but there's Bean Cave, there's where they mine it, and Coronach, do this kind of stuff. I don't know the exact location of boundary down and stuff like this. Anyways, but here's the idea. The general idea is that there's coal being burnt, heats up water, right? That steam then goes through here, twirls this turbine, which twists the magnets. So as long as you've got moving magnetic stuff and wire involved, copper wire, you're generating electrical current. They're related phenomena. But then that water comes back as it's cooled, returns into liquid form of water, and then the whole thing, the water could be just reused again. Okay. There's a picture. Biomass. So, renewable resource is organic. Made up of, it's a renewable resource. Organic, made up of plant and animal waste. Wood, shavings, peat, straw, nutshells, sewage, oat hulls, biomass. Organic waste decomposes to produce methane gas, and that can be burned. So once again, you got pollution to boil water and make steam. And it's used to turn the turbine. The most common biomass is wood. Nuclear energy can also be used from a thermonuclear generation through heat energy in nuclear energy stations. We don't have them here. We're talking about possibly building them because we have incredible uranium deposits up north, very close to the border of the north end of Saskatchewan. Uranium City. It's not a city. It's wishful thinking. They never got there. It's like White City, but White City is way bigger, but it's not a city. It probably will be someday a small city. And then nuclear reactor. Atoms of a heavy element, usually uranium, are split in a chain reaction. This splitting is called nuclear fission. Releases an enormous amount of energy. The nuclear fission of just 1 kilogram of uranium is equivalent to burning about 50,000 kilograms of coal. So that's a good thing. Way less. The heat energy released by the fission process is used to heat water to produce steam and turn a turbine. Nuclear energy is generally considered a renewable resource. However, the uranium ore necessary to produce fission is not renewable. Once it's used up, it cannot be replaced. So I don't even understand that statement. Why they say it's generally considered renewable. Saskatchewan is currently the world's largest uranium producing region. accounting for 30% of annual uranium production in the world. There are several uranium mining operations in the province, including Eagle Point, McLean Lake, and McArthur River. Saskatchewan does not currently use nuclear energy to produce electrical energy. There continues to be research to determine if that makes sense as a future electrical energy source for the province. Geothermal energy. That's just lucky where you are geographically. Some places in the world, water heated by molten rock at its core rises to the surface as hot water and steam. This renewable energy source is called geothermal. Geothermal energy sources at or near the Earth's surface are hot enough to heat homes and other buildings. However, for generating electrical energy, hotter sources. High-temperature geothermal sources are found deep in areas where there's volcanic activity. So in a way, we're lucky we don't have that because we don't worry about volcanoes blowing. Right? Iceland, with its many active volcanoes and hot springs, uses geothermal energy to produce 19% of its electrical energy. In Canada, geothermal sources hot enough to be used to drive turbines for electrical energy generation are located in BC. Research is being done to determine how to use geothermal sources cost effectively. And other energy sources. Solar energy, you've seen solar panels, right? It's more and more. Some people have them on their houses. Sometimes there's solar fields. Many people think solar cells are new technology, but no, this goes back to 1839 when a French scientist, Edmond Becquerel, soaked two metal plates in conducting solution. When he exposed one of the plates to sunlight, he could detect a small amount of voltage between the plates. He had invented the first solar cells. Solar cells are now made using silicon. There's a diagram if you're interested. Wind energy. I think we understand this. It's twisting. What's moving the magnets? The wind, right? Still the same thing. Tidal energy. Since we don't have an ocean, it's not very possible for Saskatchewan to have tidal energy. But you guys understand the idea that the tide goes in, the tide goes out. There's water moving. It's not rapid, but North America's only tidal energy generating station is Annapolis Royal, Nova Scotia, where the powerful tides of the Bay of Fundy spin turbines. Water goes in, water goes out, and it moves. And it provides enough electrical energy for about 4,500 homes. So it doesn't solve, even that's a small province, and it doesn't solve all their problems, but it contributes to some clean energy. Tests are underway in Nova Scotia and BC on a promising new technology called tidal steam generator, which works like an underwater windmill. Other marine energy sources that are being tested include ocean wave energy and ocean thermal. Okay. Now, in Canada, I'm going to stop here because we still need to summarize something. Back on that 272. I have a little simplified diagram. You know how they had the like actual homes, stuff like this, right down here. They had the generator station. They had a building there, power line, substation, sends it out to all places. This is a good enough summary, I'd say, if you understand. You've got a generator station. Maybe I'll just actually change that to generator station. Just station. I'll make it small. So that it actually fits. Power lines, I think you can read, substation, homes, etc. The magnets in an electrical generator are rotated by a turbine. And it doesn't matter if it's coal, gas, hydro, whatever, you've got moving magnets. So we're not worried about what type it's sent out. I want you to understand that. I'm glad you guys so well. I think we were getting something out of the reading together. Okay, I'm going to just record this last little bit. This is what we're doing in the next day. Do you have a camera, Noah? Take a picture of this because tomorrow, what's that? Oh, it's frozen. Well, there we are. Read 272. This is tomorrow. 272 through 79. It's another textbook day. Explain what the following energy sources are about. We're going to do that tomorrow. And then some catch-up work, too. If you're missing something, you could do these as alternates if you didn't get this to me yet. If you did do it, you don't have to worry about this because it's the same information that we did in the activity. That'll be tomorrow. Friday yet to be determined.